fine. Okay. But it's not.
Oh, you haven't plugged in the. Where's like you plugged in the. Oh. You're duplicating the screen. You need to have one screen. Not extend, but duplicate. Sorry.
It's how to do. You can
You could drag it over. I just want to be able to see it. System settings. Go to system preferences. Display. It's up there now.
Oh, sorry. Oh.
Display settings. Display.
Okay, I'm not able.
We just send it to somebody else. Where does it? How do we do this in Mac? I don't. Don't you drag your slides over to this side?
I have no idea.
You can stand here. Very sense. Slides?
Yes.
Okay. Now drag it. Yeah. There we go. Okay. Now make it big.
Hello.
You want to share the screen? No. Share. Go to Zoom. Zoom extended screen. This one. This one. Share.
But I'm not able to see.
Yeah, you don't see.
I'm not see.
Good to go. All right. So our second and final speaker of this session is Rajendra Kumar, who's going to be talking about improved classical and quantum algorithms for shorter spectrum problems. Please take it away, Rajendra.
Hi. Okay. Hello, everyone. I'm Rajendra Kumar, and today I will talk about improved classical and quantum algorithms for the shortest vector problem via bounded distance decoding. So this is joint work with Divesh Aggarwal, Yanlin Chen, and Yixin Shen. So before talking about the shortest vector problem, let's look into the motivation of studying this problem. So the main motivation comes from the post-quantum crypto. So what I mean by post-quantum crypto is the crypto systems which runs on the classical computers, and they are secure even after quantum computers. And we know that most of the current decrypto systems which we are using right now, their security is based on integer factoring or discrete log problem. And due to source algorithm, we know that these problems can be efficiently solved by quantum computers. So today we can't decline the fact that in next 20 years or 30 years, we might have a quantum computer set. So looking into this scenario, we need the crypto systems which are secure even against a quantum adversary. And towards this direction, NIST announced a competition for post-quantum crypto standards in 2016, which is currently ongoing. And in this competition, most of the candidates in the final round are lattice-based. And it makes the lattice-based cryptography the most popular candidate for post-quantum crypto. So what is lattice-based cryptography? So it's like you're designing a crypto systems whose security you want to based on lattice problem. And most of these lattice problems are conjectured to be secure against quantum adversary. And we get something more here, which is like we can get the crypto systems whose security can be based on the worst case hardness of a lattice problem. So mostly in cryptography, we get the hardness we get the security from the average case hardness of a problem. But in lattices, we can reduce those average case hard problems to the worst case hardness of some different problem. In our case, we can reduce, you've seen in the previous talk that we have problem like SIS, LWE, on which we design the crypto systems, and we can reduce those problems to the worst case hardness of other lattice problems that we'll see in this talk. And not just post-quantum crypto, we get many other powerful crypto primitives which were not possible without lattices. One of the example is fully homomorphic encryption, and the first construction was given by Gentry in 2009. So all these properties make lattice-based crypto a most prominent candidate for post-quantum cryptography. So not just crypto, lattices have many other applications. In number theory, lattices are used for factoring polynomials over rationals. They have applications in integer programming. We can also use lattices for cryptanalysis. Few examples are an AppSec crypto system and variant of RSA. And very recently, lattices are used to show the average case hardness of K-sum problem. So these are the few other algorithmic applications of lattices. Now we have seen why we want to study lattices. Let's talk about what is a lattice. So a lattice is a grid-like structure, and it's defined by a set of basis vector. So a basis is a set of linearly independent vectors. So given a set of linearly independent vectors v1 to vn, a set which contains all the integer linear combinations of these vectors forms a lattice. So, and throughout this talk, I will use n to denote the rank of the lattice. Here, rank is the number of linearly independent vectors in the basis. So in this diagram, you can see U1 and U2 generates this lattice, and we can also use V1 and V2 to generate the same lattice. So, but by just, if you are given the basis as a U1 and U2, we will get some information about the geometry of the lattice. But if you are given just V1 and V2, it's very hard to get any information about the geometry of the lattice. So the output, so the input of the lattice gives you, it's possible that the input of the lattice gives you very less information about the geometry of the lattice. So let's look into the most important problem on lattices, which is shortest vector problem. In this, we are given a basis of the lattice, and our goal is to find the shortest non-zero lattice vector. And we will use the notation lambda1 to denote length of such a vector. We can also define the approximation of this problem, which is like in gamma approximation of short SVP, given a lattice, given a basis of the lattice, we want to find a non-zero lattice vector whose length is at most gamma times lambda1. So now let's talk about what we know for shortest vector problem. It's easy to see that gamma SVP becomes easier for large approximation factors, and we know that this problem is NP hard for constant approximation. We know that for square root n approximation, this is an NP intersection co-NP. For cryptography, we are interested in the polynomial approximation of SVP. And if we just talk about the polynomial time algorithms, we can only get 2 to the power n log n by log n, which is almost exponential. And in this talk, we'll focus only on exact SVP. So now you might be wondering why, like, the motivation of this talk comes from cryptography, but now we are only focusing on exact SVP, which might not have any impact on the cryptography. But the only way we know of solving the polynomial approximation of SVP is by reducing it to an exact SVP solver on small rank lattices. So any improvement on the algorithms for exact SVP will also give an improvement in the polynomial approximation of SVP. So now let's talk about the algorithms for exact SVP. So there are two different classes of algorithms. One is enumeration, which is initiated by Kannan in 1987. He gave an algorithm, super exponential time and required polynomial space. The second class is given by Aitai Kumar and Shiva Kumar, which is known as the class is known as sieving. They give an algorithm which takes exponential time and exponential space. And after a series of work, Aggarwal, Dadush, Regev, and Stephen Davidovitz gave an algorithm that exists 2 to the n time and 2 to the n space. So prior to our work, this ADRS15 algorithm is also the fastest classical and quantum algorithm for exact shortest vector problem. So what we do in our work, we first give a classical algorithm, classical space efficient algorithm, or algorithm requires us 2 to the n over 2 space, and it takes 2 to the 1.669 n time. And quantumly, we are able to get a much faster algorithm. It takes 2 to the 0.835 n time and requires 2 to the n over 2 space, and 2 to the 0.293 quantum RAM and some polynomial qubits. So these are the two results about classical and quantum algorithms. And by seeing the state of the art of exact SVP, you can see we either have algorithms takes like super exponential time and polynomial space, or exponential space and exponential time. There is nothing in between. So we can hope for a smooth trade-off between these two classes, but before it, like, there is no provable algorithm known for this thing. And in this work, we also give a smooth time space trade-off for SVP. So basically, we give a randomized algorithm for SVP that solves in q to the order of n time and q to the order of n over q square space. So you can see here q is a parameter. If you take q to be square root 10, we get a super exponential time and polynomial space algorithm. And if you take q to be constant, we get exponential space and exponential time algorithm. So this is about all the results which we have in our paper. Now, in this talk, I will only focus on the quantum algorithm. So let's look into this reduction. The first component, the first component of our algorithm is discrete Gaussian sampling. So what is discrete Gaussian sampling? We want to sample a vector from a lattice, and where the probability is proportional to exponential in minus pi times the norm of the vector square divided by s square. So here s is a parameter. You can see if we decrease the value of s, we'll get a more concentrated distribution. So here you can see many example of the Gaussian distribution where the y coordinate represents the probability density function for the vector. So what we know about the hardness of discrete Gaussian sampling, we know it's easy to do when the parameter s is large, and it has applications in learning with errors, and it's used to design the digital signatures. For small value of s, it's very hard to sample, and if we are able to do it, we'll be able to solve SVP. And there is something in between which is smoothing parameter, and so smoothing parameter is the smallest value of this width s, such that if you sample vectors from if you sample a vector from a continuous distribution with width s and then take modulo L, then it will be equivalent to a uniform distribution over modulo L. So what we are able to do for discrete Gaussian sampling, we give an algorithm that says that we can output m samples from distribution or discrete Gaussian distribution at width smoothing parameter in m times 2 to the n over 2 time and 2 to the n over 2 space. So you can see the time complexity depends on the number of samples you required. So we will see how this algorithm will help us in getting a faster algorithm for SVP. So let's look into the second problem, which is bounded distance decoding. What is bounded distance decoding? We are given a lattice and we are given a target vector with the promise that the target vector has a lattice point which within a distance alpha times lambda 1. And with this guarantee, we want to find that closest lattice point. And so Dadu, Sergey, and Stefan Davidovich gave an algorithm that gives a relation between bounded distance decoding and DGS. They show that we can solve 1 over 10 cube approximation of BDD by using order of q to the power 18 n over q square independent samples from DGS at smoothing. So now you can see how we'll use the DGS sample to solve the BDD BDD problem. So now let's see how we can we improve this lemma in quantum. So let's see how this algorithm actually works. So first of all, like we have to define a dual lattice. So a dual lattice is contains all the vectors in the real space such that the inner product with all the lattice vectors is integer. So we can, so they define, so the motivation of this work, the idea of this work comes from Aronoff, where I gave a periodic Gaussian function, which is the ratio of Gaussian mass of the shifted lattice divided by the Gaussian mass of the lattice. So this thing, as you can see, they show that this is equal to the expectation of cos of 2 pi times inner product of W and T, where W is sampled from discrete Gaussian over dual lattice at smoothing parameter. So by the second expression, you can see that this achieves the maximum value when W is when T is a lattice vector, because if T is a lattice vector, W times T will be a integer, and that time the f of T will get the maximum value. So this is how the function looks like. So it achieves the maximum value when we are at the lattice point. So kind of f of T gives us some information that how far we are from the closest lattice vector. So what they do, they try to do a hill climbing process to go to the nearest lattice vector by updating the target vector. So what they use, they apply the formula T plus the partial derivative of f of T divided by 2 pi f of T, and they show that within a constant number of updates, we will reach the target, vector if with some promise of the BDD problem. And so, but you already seen that this f of T is a exponential, or it requires many samples. So we can approximate the value of f of T by using a finite number of samples from this dual lattice. And so for a large value of samples, f of T and f of WT is, the difference between these two quantities is very small. And what we do in this work, we use the idea of quantum amplitude estimation to get the same approximation of FWT. We get the same approximation of FWT in square root n time. So classically, it requires order of n time. Quantumly, we are able to do it in square root n time, and that makes that can kind of have a square root improvement in the time complexity of BDD problem. So we'll see, and when we want to make a multiple calls to a BDD, when we want to solve the multiple instances of a BDD oracle, we can use the same n samples multiple times, and each time solving a BDD problem will just require square root n time. So till now we know how to solve BDD by using the samples from a discrete Gaussian sampling. And now we'll see how we can, what's the relation between BDD and the shortest vector problem. So we know that given a alpha BDD oracle, given alpha BDD oracle and integer p, we can, for any target vector t, we can sample the vectors within distance p alpha times lambda 1 by making p to the n calls to the alpha BDD oracle. So if we set t to be the origin and p to be 1 over alpha, then we'll be able to sample all the vectors within distance lambda 1. So we will be able to find the shortest vector by using p to the n calls to alpha BDD oracle. And if we have a space efficient algorithm for BDD alpha, then we'll also get a space efficient algorithm for SVP. So the idea is, if we have a 1 over 3 BDD oracle, by making 3 to the n queries, we'll be able to solve SVP. And what we show that we can get, first we get 2 to the 0.16 and samples from discrete Gaussian sampling a smoothing parameter, and these samples are slightly above the smoothing, and we require 2 to the n over 2 times to get one sample. And these samples can be reused. because every time when we are using when we are solving a BDD oracle over the same lattice but with the different target vectors, we can reuse the same. We can use the same lattice vectors. So we have 3 to the n SVP candidates. We apply the quantum minimum finding algorithm, and this algorithm takes 2 to the 0.873 n time. So this is the first. This is our quantum algorithm for solving SVP. We can also get an improvement over this by using a spherical covering technique. In this, the idea is we want to cover a ball of radius λ1. Last time we have tried to cover, we are covering this by choosing the target vector as the origin, and then we take a circle which is 3 times alpha times λ1, and if we take alpha to be greater than 1/3, then we are able to cover the radius λ1. But now we are just taking we are just making 2 to the n calls to alpha BDD oracle that will give us a coverage of 2 alpha λ1. So what we do, we choose the target vector over the smaller ball, and we know that for that ball, by making the 2 to the n calls to the BDD oracle, we will be able to cover this 2 alpha λ1 sphere. So we can by a simple geometric argument, we can say that for this angle phi, we required if we randomly choose order of sine phi to the n points on the smaller radius, we'll be able to cover the bigger circle. So by using this technique, we get a classical algorithm that runs in 2 to the 1.66 n time and requires 2 to the n/2 space. And this also gives an improvement in the quantum algorithm. It requires 2 to the 0.8345 n time, 2 to the 0.293 n quantum RAM, and 2 to the n/2 space. And the time complexity of our algorithm also depends on a quantity which is related to a lattice Kissing number. So lattice Kissing number is essentially for a lattice, the number of shortest vector is known as the lattice Kissing number. So in practice, most of the lattices has sub-exponential Kissing number. In this case, our algorithm just takes 2 to the power 0.66 n time. So this I would like to conclude. So in this work, we gave a faster quantum algorithm for SVP. We gave a space-efficient single exponential time algorithm for SVP. Algorithms take less time with a small Kissing number, and we also gave a smooth Simon space trade-off for SVP. Thank you.
Thanks for the nice talk, Rajendra. Because we're running a bit behind schedule, we unfortunately don't have time for any questions, and also because the next session is starting in just 5 minutes in the main ballroom. So let's, on our way out, we thank both speakers again and head to the main ballroom for the business session.